Hi, so what we're going to do now is take a molecule and try to be able to identify all the chiral centers and then label them as R or S. I think one of the first things that you should do is draw out all the hydrogens that are implied, right? Because that's going to help us determine whether there's four groups or not on a chiral center. All right, so on the end, if we start here on the far left, we see that there's a methyl group. So this is actually a CH3. And the first thing that we should notice is that if you have anything with more than one hydrogen, you can't be a chiral center. Right? So this isn't going to be a chiral center because we have to have four different groups. Right? And in order for us to have four different groups, we can't have more than one hydrogen. We can have more than one carbon, but we're going to talk about them as long as there's some difference. But hydrogens, since they only make one bond, tend to always be the same. As we keep going right across the molecule, we get to this oxygen. It's only got two bonds, so not a chiral center. This next one, we have a carbon, and we have a methyl group that's wedged. And because that one's wedged, it means the hydrogen implied has to be dashed. Now, this one, I think we do have a chiral center, right? Because if we circle this to indicate it, if we count the different groups, we have an oxygen, so that's one. We have another carbon, that's two. And now we go to this third one, and that's a carbon. But this carbon here is different than the carbon we were just at, right? You can say this one's a methyl group, the other one's part of a carbonyl. So as long as you can find some difference between the two carbons, you can say they're different. And then we have a hydrogen. Alright, so that's our first chiral center. So let's go through and find all the chiral centers, and then we'll come back and label them as R or S. Alright, as we keep going across the molecule, the bottom one has a CH3. We said if there's more than one hydrogen, we can't be a chiral center. If we come back up here, we have a carbonyl. We have two bonds to an oxygen, so we can't be a chiral center. Anything that has a pi bond, so a double bond or triple bond, cannot be a chiral center because we have to have four different groups, and this is only going to be bound to three things. 1, 2, 3. So it can't be our chiral center. Same thing for the benzene ring. It makes the benzene ring really easy because each one of these carbons is attached to a double bond, so we have no chance to be a chiral center. So all 6 of these carbons are not chiral centers. Same over here. We have a chlorine that's wedged, which means the hydrogen implied has to be dashed. And now we look at this one. There's a carbon to the other side, but there's still some difference, right? This one has a double bond as part of it. This is just a CH2 group. So as long as there's some difference between these two carbons, we can say that they're different groups. Chlorine, hydrogens, we have our 4 groups. So let's mark this one with the red dot to show that that's a chiral center. Alright, this next one is a CH2. So since we have 2 hydrogens, that's not a chiral center, right? So we can keep moving along. Now we have this amine up here that's dashed, which means that the hydrogen implied has to be wedged. Alright, so if the one group that's already on is already wedged, then the next group has to be dashed, and vice versa. If the group on there is already dashed, then the other group has to be wedged. Alright, and then the same here. The nitrogen is different than the hydrogen. We have 2 carbons. We have a carbon that's attached to a carboxylic acid and a CH2 group. So yes, we have 4 different groups. We label this one. The nitrogen has 2 hydrogens, so we can say no and move on. And then the carbon at the base of the carbonyl is attached to a double bond, so we can say no. Alright, so this one has 3 chiral centers. So if we go all the way back to the left, the first thing we want to do is start numbering them. Alright, so we want to do the highest priority. And the highest priority is looking at the atoms directly bound. So this is our chiral center, so we want to look at the 4 groups attached to it. So it's going to be this carbon, this oxygen, this carbon, this hydrogen. And we're going to rank them based on atomic number. Alright, so the bigger number, the higher priority. So the first one would be the oxygen. And now we have two carbons, right? A carbon at the base of the carbonyl and a carbon down here. Since they're tied, since they both have the same atomic number, we look at which one it's attached to next. So we take this carbon and we look for the biggest thing it's attached to. It's an oxygen. We look at the bottom one and we look at the biggest thing it's attached to is a hydrogen. So since oxygen is bigger than hydrogen, it wins. So this becomes 2, 3, and then our hydrogen is 4. Alright, so then lastly, you always want to make sure that your lowest priority, so whatever you've labeled 4, is going to be going away from you. Right? And that means dashed. And so in this case, we're in great shape. The hydrogen's going away. So which means we can just take our numbers, go in order, 1, 2, 3. We're going clockwise. So this is R. Alright. Let's try another one. We see this chiral center over here on the right. We have a chlorine, so that's going to be 1. We know our hydrogen is going to be 4, right, because it's the smallest. And now we have the same problem. We have 2 carbons. So now we're going to take this carbon and look for the biggest thing it's attached to. It's another carbon. Do the same over here. The next biggest thing that's attached to is a carbon. And so since it's a tie, we go back. And now we'll look for the second biggest thing this is attached to. Since this has a double bond, we can go to it again. So it's still a carbon. This one, the next biggest thing is one of these 2 hydrogens. Alright, so that means this carbon over here on the left is going to win. So that becomes 2, 3, and then the hydrogen was already 4. Once again, the hydrogen's going away from us, so we're in good shape. And so we just go in a circle, connecting the numbers. So it goes 1, 2, 3. And we can ignore the 4 because it's going away from us. It's going back into the plane of the board or the paper. And so now we're going counterclockwise. So that tells us we're S. So this chiral center has an S configuration. Alright, and then this last chiral center, we have a nitrogen, a hydrogen, and then the same 2 carbons. Alright, so let's number this. The nitrogen is going to be 1. Now we have the 2 carbons. Same idea, we want to compare them. This carbon's attached to an oxygen. This carbon, the biggest thing it's attached to is another carbon. So the oxygen is bigger than the carbons. So this becomes 2, 3, and then the hydrogen is 4. So if we draw our numbers, so now that we've numbered everything, the biggest thing is double checking that the lowest priority is going away from us. Alright, so in this case, the hydrogen is going the wrong direction, right? It's pointing towards us. Alright, so a neat trick we can do is we're still going to go ahead and solve for the direction that the letters or the numbers tell us in. So if we look at our numbers, it goes 1, 2, 3. So it's going to go in this direction. Alright, so it'd be clockwise. So typically we would say the answers are, but since this one is going the wrong direction, that's going to cause us to flip our answer to S. Alright, and the reason we can do that is essentially we're looking at this backwards so we can flip it over. Alright, and so the reason we have to flip this answer is because the lowest priority has to be going away from us, which means typically it's dashed. Right? And since it's not dashed, it means we're not looking at it from the right direction. And so that's why a neat trick that we can do is if this is wedged, is that we can just flip our answer from R to S or S to R. Now, if the lowest priority would have been in the plane, then we have to redraw the molecule. So we need to rotate it to put that lowest priority going away from us. Alright, so make sure that you're really careful that the lowest priority is going away from you. Alright, a couple things just kind of overall view. Remember, to be a chiral center, you have to have 4 different groups. So that's the take-home message. If you're just looking at a molecule and you're trying to find a chiral center, it's got to have 4 different groups attached to it. They can be the same atoms as long as there's some difference in them. And what we saw a lot in here is carbons, right? As long as it's a methyl versus a carbon at the base of the carbonyl, or a methyl versus ethyl, those are good enough to be called different, and so that works. Alright, once you find a chiral center, label it the priorities. Based on the larger the atom, the higher the priority. And then lastly, make sure the lowest priority is going away from you. Now, the last thing we're talking about is this one has 3 chiral centers. Right, so let's write that up here on top. So we have 3 chiral centers. The way you could solve for how many stereoisomers you have is you can use the equation 2 to the n, right, where n is equal to the number of chiral centers. Now, when we're doing this, we want to plug it in for n on top, so you actually get for this problem n to the third. And remember, that really means 2 times 2 times 2, which equals 8, which means we have 8 possible stereoisomers. And where the 2 comes from is at every chiral center we have a choice between R or S. So if you're going to draw all the stereoisomers for this molecule, you could draw 8 of them.